Right, today we're going to talk about chapter 21, and this will be the last chapter that we cover in general chemistry, and then we'll have a couple weeks on biochemistry, and then that'll be it for the semester. So, what is a buffer? So, a buffer solution is something that is going to resist changes in pH. These are really important for biological systems because a change in pH can cause denaturation of proteins and them to lose their function, and then for the organism that those proteins belong to can die. A good example of a buffer inside of you is actually in your blood. So inside your blood you have a buffer, a bicarbonate buffer, and it works like this. So as your blood moves through your body, it picks up CO2 from your cells and drops off oxygen. Your blood cells have a heme group, which is a protein at the center of them, which is specially designed to carry oxygen, but it doesn't really carry CO2 as well. So the CO2 just dissolves into the liquid inside your cells. But it has two purposes. First of all, it's getting rid of CO2. When the blood gets to your lungs, it deposits the CO2 and picks up more oxygen. But also it acts as a buffer and protects you against pH changes. So for instance, if you had a increase in acidity in your blood from, let's say, eating something acidic or eating meat, you would see the entire reaction going this direction. Because you'd see a change and you'd see an increase in the concentration of H plus in your blood. Therefore, you would see the overall reaction start to head towards the left, and CO2 gas and water would be produced because it would be trying to decrease the concentration of H2CO3 as more H2CO3 was being made. And it's a chain reaction, as you can see here. So when you don't have a functioning blood buffer, you can get something called ketoacidosis, and it is a life-threatening condition. It's something that diabetics have and can have an issue with. So, but a buffer is made of a solution of a weak acid and its base. So in this case, we have a weak acid, which is H2CO3, and then we have its conjugate base, which we learned about last time we talked about acids and bases. And then we also have, and this is a diprotic acid right here, this H2CO3, because it actually has two conjugate bases that it can have, so it can actually give off two hydrogens. And so as you increase hydrogen in the system from diet, then the hydrogens, because it's a weak base, so it has a small, very, very small Ka going this way. Therefore, Kc going this direction is actually very big. So therefore, when you put more, you increase the concentration of hydrogen, you are going to have it 100% the reaction go in this direction. Because if you remember, the K for a reaction, if it's equal to, so K is equal to a number, then the K reverse is equal to the reciprocal of that. So if K in this case for carbon, I don't know what the the K is for this, but it's small. So let's say K is 1 times 10 to the negative 4th power. Then the K for reverse would be 1 over 1 times 10 to the negative 4th power, which 1 divided by 10 to the negative 4th is equal to 10 to the 4th, which is 10,000, which is really big. So another example of a buffer would be one with acetic acid, which is in vinegar. So we got CH3COOH plus CH3COO minus H3COO minus CH3COOH. Okay, so notice that the reactants and products are the same on each side. So when you add, the reason buffers work is because you have no net change of products and reactants because they're the same. That does not work, for instance, with HCl plus NaOH. The reason it doesn't work is, first of all, these are both strong bases, or strong base or strong acid, and when you come to the side you have different species. Okay, so these are different than the reactant side, whereas these ones are the same, and that's what gives buffers their ability to resist changes in pH. So if we look at what's called a titration curve for each of these, which is just when you graph the pHs when you do a titration. Now, the titrations that we've done so far have been with a strong base and strong acid. So if we would have, when we did those titrations, and we would have measured the pH for every 5 milliliters of base we added, we would have seen the curve would have looked something like this. And then this would be called the equivalence point. Now, what you would have here is, so this is your pH on the left-hand side here, and this would be your milliliters of base. And the pH would stay very, very low, even as you added base to it, until you got to almost done with the base, and you would get to the equivalence point. It would be a 7, then after that the pH would just shoot up. On the other hand, the pH curve of a weak acid looks something like this. And here you would have what's called the midpoint, which is when you would have the amount of HA would be equal to the amount of A minus. That is the midpoint, and your equivalence point would be here, which was when the amount of A, well, I'll write it this way. The amount of HA would be equal to the strong base, because we would be titrating this with a strong base. And that would be the equivalence point. But what you have here is you have a smaller curve, and this area here is called the buffering region. And this is the region where it would resist pH change. Once you get outside this region, now you've used up all of your buffer, and you would have your pH shoot up. So, for instance, this graph I drew is for acetic acid, which is the top chemical equation written on the board here, and its buffering region is between about 3.5 and 5. So that's what the pH region here, that it would prevent a change in pH. So the only way to really appreciate the buffers is to look at it mathematically, and then you'll see, unless we were able to actually do a titration, which we were supposed to do a titration of a weak acid and see this, but the pH meters that we had weren't the highest quality. So we have to just calculate it out to see how this works. So there's an equation for that applies specifically to buffers, and that equation is pH is equal to the pKa plus the log of the concentration of the conjugate base over the acid. Now, if you remember what pKa is just going to be the log of the opposite of log of Ka. So if you have the Ka, you can always find the pKa. So for an example, if we wanted to find the pH of a solution of acetic acid buffer, and let's say we had 0.25 molar CH3COO minus and 0.15 molar CH3COOH, well, we would, and the pKa for this is 4.75, we would just write the pH is equal to 4.75 plus the log of 0.25 over 0.15, because this is a ratio, we're just taking the log of the ratio, and we would find out that it equals to 4.97. And that is how you use this equation. So it's real simple. So let's just say, though, we wanted to make a 0.1 molar solution of phosphoric acid buffer. So we want to use Na2HPO4 and NaH2PO4. Now, phosphoric acid is a triprotic acid. It has 3 hydrogens it can give off. But in these two forms, in this form, it has 1 hydrogen it can give off, and this one can have 2. So therefore, in this case, this one is the acid, and this one is the base. So we want to make a 0.1 molar solution, but we want to make it so it has a pH of 7. And the pKa for this acid is equal to 6.86. So how do we figure this out? Well, we know we want the pH to be 7. We know the pKa is 6.86. The only thing we don't know is the log is the ratio of the two species. So what we're looking for is to find in what or how many grams, I guess, we're going to put into the solution of the basic version and the acidic version. So I like to write it like this. I'm sorry about that line. I don't know why it does that. And then we do 0.1 minus X down here. And the reason I did that is because we want a 0.1 molar solution. Therefore, the concentration of, if I wrote it like over here, if this is A minus, then then HA is at the bottom. This would be the same as saying that A minus is going to be 0.1 minus A minus, because that's how much HA will be left over. So I have my expression set up now, and now we can solve for this. So the first thing I would do is subtract 6.86 from each side, which is going to give me 0.14, because 7 minus 6.86, and that's going to equal the log of x over 0.1 minus x. Next step we need to do is get rid of the log. So if you remember, if the log of x is equal y, then 10 to the y is equal to x. So using this, we can raise each side. So we can raise 10 to the 0.14 and 10 to the log of x over 0.1x, and what that's going to leave us with is 0.138 is going to be equal to x over 0.1 minus x. It gets rid of the log. Well, now it's pretty simple algebra from here. So we can multiply both sides by 0.1 minus x. And what we will have then is going to be 0.13 I'm sorry, this number right here should be 1.38. If you raise 10 to the 0.14 power, you get 1.38. So over here now, if we multiply this, we'd have 0.138 minus 1.38x is equal to x. Now we just subtract x from each side, and we're going to have 0.138 minus 2.38x. So now we can come over here and put positive 2.38x on this side is equal to 0.138 on that side. Divide both sides by 2.38, divide by 2.38. We find that x is equal to 0.058. Now this is going to be in concentration in moles per liter. So given the top here, we know that because this is the base on this part of the equation, we know that this is the amount of moles of base we need. So to find the grams of Na2HPO4, we just take 0.058 and multiply it by the molar mass, and we're going to need 8.2 grams, and that's per liter. Now to find the amount of the acid we needed, we look to the bottom of our original equation right here, and that is going to be 0.1 minus 0.058 multiplied by the molar mass, and that is going to be equal to 5.8 grams, and that's going to be per liter. So if we wanted to make half a liter of buffer, we would divide these two numbers by 2. Now if we look at this, I took 0.1 minus what x was, and I got that from here because we want our total molarity of the solution to be 0.1, and that's important when you're making buffers for like cells and you're doing biochemical research or you're doing microbiology or biochemistry, because if you mess up you can have the right pH that a cell can survive in, but if you have the wrong molarity, then you can still kill the cell, and we don't want that. So that's why when you're making buffer solutions, and this chapter is a good transition into biochemistry, because when you're making solutions of buffers, it's important to have the molarity right and the pH right. Otherwise, you're going to kill, or if it's not alive, you're going to destroy whatever you're trying to preserve. And the point of buffers is to preserve something. All right, so now to demonstrate the power of a buffer to resist, we're going to add to that solution. So we have pH is 7 of phosphoric acid buffer solution, and we are going to add 2 milliliters of 1 molar HCl. So now we're going to see what the pH would be after that. So the pH is going to be equal to 6.86, the pKa, plus the log of base over acid. Now, previously we saw that we had our ratios were 58 and 42, and this is going to be millimoles. Basically, I just took the numbers that we had from last time and multiplied them by 1,000. You'll see that these two add up to 100, which is what we want. So now, because we are adding 2 milliliters of 0.1 molar solution, to find out how many moles that is, we would just multiply the 0.002 liters times 1 molar, and that would be 0.002 moles, which is equal to 2 millimoles. So what I'm going to do now is we're just going to, because it's acid we're adding, it's going to be 58 minus 2 millimoles from the top, and it'll be plus 2 millimoles to the bottom. If we now solve this, we will find that the pH is going to be equal to 6.96. So it's a little bit of a change, and we're going to find that this change is going to be a change in negative 0.04. Now, I'm going to show you something. What if we would have just added 2 milliliters of 1 molar HCl? And now this was to a 1 liter solution of buffer. If we just added 2 milliliters of 1 molar HCl to pure water, what would the pH have been? Well, the pH for that would have been pH is equal to the opposite of log of the concentration of H+, which would have been the opposite of log of 0.002, and the pH for that would have been 2.7. which is a difference in negative 4.3 pH units. That's 10,000 times more acidic. That shows you the importance and the power of buffers. So the same amount of acid in pure water would have made the acid 10,000 times more acidic, whereas with the buffer, it hardly did anything at all. So let's take a look at, we'll do another example with just the original equation here, but we'll add base to it this time. So starting with the same buffer solution, this time we're going to add 6 milliliters of 1 molar NaOH. So if we want to find our pH, the pH is going to be equal to 6.86 plus the log. Now, originally we had 58 millimoles, and then in the bottom we had 42 millimoles. Now, on the previous page, we actually had the number of moles. So it was 0.058 over 0.042. Now, because we're taking the log of a ratio, 0.058 divided by 0.052 is equal to 58 divided by 42. So it's okay to simplify by just writing 58 and 42, and this is a unit of millimole. Well, this is a unit of mole, because it's going to be the same as long as you, now what you cannot do is if you have 0.058 and 0.0042, you cannot in that case go 58 over 42 because those are not equal. But it would be okay to go 58 over 4.2 because you're just multiplying each number by 1,000. Okay, so this time we're adding 6 milliliters of 1 molar base. So 6 milliliters, since that is 1/1000th of a liter times 6, and it's a 1 molar solution, so it's easy, that's going to be 6 millimoles. Now because it's base, we're going to add the 6 to the top. So we're adding 6 millimoles, and this one will be minus 6. Because if we had the chemical equation here, so H2PO4 plus HPO4, because we're adding base, it's going to push the reaction more towards, you're going to have a higher concentration of this because we're taking off one of these hydrogens. So we're adding base, the base goes to the top, and now when we solve for this, we find that the pH is going to be equal to 7.11, which is a change in positive 0.11 pH units, which is very, very small, which is acceptable for most biological systems. Now, had we just added 6 milliliters of 1 molar sodium hydroxide to a liter of pure water, the pH would have been 11.78, which is a change in positive 4.78. You nor any other living cell could survive that. That is bad. However, you can survive this, which is why we have buffers and they're so important. Okay, so that's it for the buffers chapter. It's not nearly as long, and then next week we'll look at some biochemistry topics and we'll probably talk about buffers again. Have a good week.